right, good afternoon. So I think we're right after lunch, so hopefully people are not falling asleep. We're going to be talking about Hadoop hardware at Twitter, and size does matter. You have to.
Good.
So my name is Joep Rottinghuis. I'm a software engineer at Twitter. That's how I started, and at the moment I end up managing the Hadoop and HBase teams there. You can follow me at Joep.
And I'm Jay. I'm a hardware engineer. I work with the Hadoop and other teams. Follow me at EEcraft. And for this type of work, there's a lot of people involved, the entire Hadoop and hardware teams and many other people. It really takes a village to do something like this. Back to you.
Yep, so we are the one who can present, but it's lots of work behind the scenes of a lot of other people that are involved. So today's agenda is about hardware at Twitter. So a lot of you may ask yourself, what kind of hardware is appropriate for clusters, and for what kind of use cases is what kind of selections do you have to make? Is it about memory? Is it about network speeds, the number of cores, the number of disks, the sizes of disks? And we ask ourselves exactly these kind of questions, and these are some of our findings. So first I'm going to talk a little bit about scale of Hadoop clusters. Then I'll talk a little bit about having a single large cluster or multiple smaller clusters, and in what cases these things are appropriate and how we're finding it. Then I'll go into a little bit of the approach that we have taken into splitting our clusters. Then I'll hand it over to Jay to talk about some hardware investigations for what's appropriate for which of these cases, and then we'll share some of the results with you. So this diagram kind of shows on an exponential scale the number of nodes. So along the bottom you see the number of nodes. And then the line you can kind of imagine being the pain involved in running and managing these kind of clusters. So for fairly small clusters, it's not that big of a deal, and as you grow in, it gets a little bit harder. And then around, roughly where you see the wall is where you end up hitting somewhat of a wall in pain. And what are some of the scaling limits that you would encounter? So there's not really one hard and fast number where clusters don't work anymore. There's multiple factors involved. So one of these factors is when on the job tracker you end up running tens of thousands of jobs in a day and tens of thousands of concurrent slots that are executing at the same time. That ends up putting a lot of pressure on the cluster, and at some point that becomes very painful and hard to manage. And similarly on the name node, if you're around 250 to 300 million objects in a single namespace, and keep in mind for an object that is a file as well as blocks that are kept there and directory objects, then things become somewhat painful on the name node. Particularly what seems to happen is when your name node reaches about 100 gigabytes of heap space, then the full garbage collection pauses that you inevitably have become somewhat difficult, because they end up doing stop-the-world garbage collection at certain phases. And if you're not careful, then your data nodes time out. The name node will conclude that part of your cluster is dead. It will discard those nodes, will try to re-replicate, which actually puts even more pressure on the name node. So those are bad situations, and it becomes very painful. And another aspect that you have on very large clusters is that when people launch jobs, with every time you launch your job, whether it's through the job jar itself or the lib jars, those jars have to be shipped out to a large number of nodes if you have running on many desks at the same time in parallel. So that can take a significant overhead on your cluster. And then finally, one of the aspects, and we talked a little bit about this morning with hrefn, is if your job history server keeps hundreds of thousands of files, then just skipping through these hundreds of thousands of files all becomes very painful. So this is where, on the scaling side, things become somewhat painful. So then the question kind of becomes, do you want to have one large cluster or lots of little clusters? And in principle, I'd like to say that we try to drive to have as few clusters as possible. Ideally, if you could just stick things together, then you would have them in one large cluster. There are some reasons for that, and there's some reasons why you don't necessarily want to do that. So one of the reasons why you may want to combine your clusters or keep a larger cluster is because a lot of times you have like shared common logs or shared common data that everybody wants to access. So if you chop things up into 10 little pieces, then you may have a repeated set of information, and then even by splitting off a different cluster, you may already be a high percentage full right from the bat. The other part is on the fragmentation side of the free space that's available on the cluster. If you have lots of little clusters, then that free space is on each individual cluster, whereas if you're shared, that free space is shared more. It's just the normal fragmentation considerations there. And in a sense, if you have fewer clusters, there's less overhead in managing these clusters. You don't have to roll to a new version on 15 different machines. The flip side of that is that there's more customers involved when you do have to do some of these larger kind of maintenances. And then finally, there's an aspect of rack diversity. So depending a little bit on the size of your cluster, if your entire cluster is just in 4 racks, and you have an issue with the top of the rack switch, that means that a quarter of your cluster is offline. Because if your cluster is much, much larger, then if you lose a TOR or you lose a rack, or you lose an entire row, then that has less of an impact. Now, on the flip side of this, there's the aspect that there's varying SLAs that you may have. So different customers may have different requirements on what they want to see out of the cluster. Some people may want to run ad hoc jobs, other people may want to run production jobs. There's other angles that you can kind of differentiate your jobs in. Some jobs are very storage intense. They require a lot of files or very large files. Other applications may be more processing and CPU intense and I/O intense. And some other jobs are maybe more network intense. And then there's the final aspect that you can consider with these things is what kind of data access there is. Some of the data is hot and maybe warm, or sometimes maybe data can be cold. So this is the architecture that we ended up with at Twitter. On the left-hand side, you'll see people that are engaging with Twitter. And through Twitter front-end servers, messages are scribed in. There's quite a few. There's a few 100 billion messages that come in a day, and they're scribed into our RT clusters. That's where logs are combined on an hourly fashion and then shipped over to our processing cluster. Our processing cluster is where we keep just about 30 days worth of data, and all the production jobs run. So only jobs that have explicit approval are allowed to run on that cluster. On the top side, you see our databases. And there's data imported from the databases into various HBase clusters. And they're also backed up to a backups cluster. The backups cluster is purely just stored snapshot data where there's no MapReduce data running there. And then aggregated logs and produced result sets from the processing cluster go 2 directions. They end up going back out to the left to the RT clusters, and they're served up there to production servers. And they end up getting copied over to the data warehouse cluster, where a much larger volume of data is stored for a longer period of time. And then the final cluster I haven't mentioned yet is on the bottom side, is what we call a cold cluster, where data that is not accessed very often, or they're much older in age, they're pushed into the cold cluster. So you can see we have various clusters with different kinds of access and different kind of requirements.
Thank you. We'll look into some of the hardware investigations we have done, what we used to have, what we have tried out, and the stuff that we're still trying. Let's start by talking about the service criteria for hardware, because this does actually shape some of our choices. First of all, Hadoop really doesn't need live hard drive swap. This influences what form factors we can pick. The second factor, which is actually sort of related to the first one, is at Twitter, we really don't have any sort of service levels on data nodes. We have gotten very good at breaking individual servers, so we don't even try to keep them up. What we do guarantee is that at the rack level, we sort of have a SLA that says that only one rack can be down at any time in a cluster. That is what we pay attention to. So this sort of does influence what type of hardware we choose. And let's start from where we were like a year and a half ago in terms of Hadoop's, like the hardware used for Hadoop. As you was mentioning, we really did have like one Hadoop cluster at the time, and we certainly had one type of Hadoop server at the time. And if you had to pick like one server to do everything, this would be still it, or something like this would still be it. The characteristics of such a server are it's a standard 2U server, 12 hard drives, 12 hot swap hard drives. You can fit about 20 of such servers into a rack. We picked a mid-range Westmere plus CPU that seemed to do reasonably well for us. We went a little high on memory than we would otherwise have. And then, of course, for networking, we picked gigabit Ethernet. This is a good general purpose server, but in a few of our applications, we have the need for a lot of storage density. And this sort of doesn't lend itself as easily to that. And then the second point is particular to the server that we had, where we thought that we had potential I/O bottlenecks. So there was room for improvement on that front. And so when we were looking for the next step, and of course this was aligned with the industry transitions to Sandy Bridge or Bulldozer, is that we could get higher CPU performance, which was a positive. We were wondering how many servers per rack we should have, and then we had the general sense that we wanted to keep all aspects of the server balanced. So if you had more CPU performance, then like what happens to number of drives to keep the CPU fed? And sort of the normal tendency is to try to increase the number of drives per server, which is what other people are doing. And then also switching to a higher drive capacity is another knob that we do have. But when it came down to it, we felt that there was too much CPU for storage-intensive applications. We didn't need this much CPU. And then, especially the aspect about putting too many drives in one server, we would end up with a server failure domain that would be too large. And we, as you remember, we don't really have any sort of SLA on individual servers. So if we sort of end up with a 24-drive server with 3 terabytes, that ends up being a pretty significant data footprint per node. So this sort of this was a logical way to go, but it posed some challenges for us. So we weren't entirely at ease with this. And that's when we started thinking about questions on like how should we do Hadoop hardware. And at the time, we were sort of the myths are now myths, at least as far as we're concerned. But at the time, they were serious questions. Are bigger servers better? That was a question that we had. And then should we continue the previous direction that we had of having one server type that serves the different applications, the different Hadoop applications that you was talking about? And given sort of the fact that we didn't want a very large failure domain, the other sort of very big thought we had was we need to get back to basics here and try to scale Hadoop horizontally and not vertically, which led us to think about what we will refer to as a Twitter-specified Hadoop server. And we actually wanted to take a slightly different direction here in going to single-socket servers. The first sort of application is for backups, where the CPU isn't much of a factor. It's much more about storage density. So picking a single-socket server like this does really help. We will talk about the choice of CPUs in a couple of slides. But we could, the point about this particular CPU is that it is also relatively power efficient. And if you equip it with 3 terabyte hard drives, you end up with a relatively small server that is relatively low power and packs a lot of storage into one server. We then also went ahead with SSD boot drive, and after a lot of thinking, we decided to stick with gigabit Ethernet networking. And this sort of makes sense for backups, because we really just want an efficient way to connect disks. But then what it turned out is that we were thinking about this was, how would such a server do for the processing? And if you recall Youp's slide, a processing cluster is our most process-intensive or CPU-intensive Hadoop cluster. And here, the CPU that we chose has fewer cores. They're much faster. The reasoning that we have is that some of our Hadoop jobs have an aspect of starting of jobs. And so if you look at like spec JVM type of benchmarks, this type of CPU does very well at startup of any benchmark. So even though we had fewer cores, they were faster, which we thought would be a positive. And then we could max out memory on this type of CPU. And that's one of the limits of this particular choice, to 32 gigabytes. But we wanted to investigate if that was enough. Then also, the proc cluster isn't terribly storage intensive, because it is a cluster that we house data for a given period of time. So we actually wanted to dial back the storage capacity of hard drives, so we went back to 1 terabyte drives, which we used to use a long time ago. And the net result of this, yes, and the other aspect is, because this is process intensive as a cluster, we decided to investigate 10 gig Ethernet for this type of application. And so what we ended up with, or what we end up with, is a relatively cost-efficient box, a relatively power-efficient box that has a lot more disk and network I/O per CPU. If you compare this with what we would have done otherwise with a large dual socket server. And in terms of rough efficiency, it seems to have half of everything, so it costs about like 60% of what we would have had with a much bigger server, which does play into some of the things that we wanted to achieve with this investigation. And then there was a third use case also for Hadoop, which was different from our general data warehouse application, which actually combines the characteristics of the previous two, in the sense that there is a lot of cold data in the data warehouse. We need a place to keep that. So disk efficiency is a requirement. There is also going to be map-reduce jobs in this cold cluster, so compute is also a requirement. So then basically we sort of ended up with the thought that we were able to try to match the first two Hadoop workloads with a very similar platform. So stands to reason that we would be able to match this workload as well. And so basically we end up with something very similar to the previous version, except we would use 3 terabyte drives, which we are already familiar with. And so we end up with a storage-dense platform that has relatively non-trivial processing capabilities. So the summary is, with the Twitter-specified Hadoop server, we have a platform that's relatively versatile for Hadoop. It seems to meet many cases, and it really meets our needs of not having a really large failure domain per node. So let's just look at what this does at the rack level, because after all, we're deploying racks and not really individual servers. So the first column is the baseline server from about 1.5 years ago, and then the next 3 columns are the Twitter Hadoop server in the 3 flavors that we talked about. And if you look at the rack level, even though the servers are very different, you end up with characteristics that are quite versatile in the Twitter Hadoop server, in the sense that you have a very similar power footprint. The baseline server is actually about 7 kilowatts, and the other ones are about 8 kilowatts. But when you look at the number of CPU sockets, you end up with roughly the same CPU sockets per rack. The CPU type is different, fewer cores that are faster, but overall compute throughput is quite comparable. The memory that you have per rack is a very important metric for us also, and we have a pretty decent handle with the Twitter Hadoop server, and we can pretty much approach what we had with the baseline. The big difference that we have is in terms of the spindle count. Of course, we can go denser with the efficient server, and so we get like twice the spindle count. So we can either use that to get a lot of IOPS at a modest cost, or we can use it to provide a lot of terabytes. And so in like the proc case, we need a lot of spindles. In the backup and cold case, we need a lot of terabytes. And so the efficient server is preferable to the baseline server in both those cases. And then finally, networking, because we also took the time to change our network uplinks to 10 gig, we have a lot more uplink bandwidth and a lot more internal to rack bandwidth that is possible with the Twitter Hadoop server. So that, at any rate, is the theory. We need to see how this runs, and I'll hand it back to you.
Right, so this all sounds almost too good to be true, so let's look at some real numbers to see what this really did. So you see a little table with some of the familiar performance tests that we have done. And the first line shows the test DFS I/O written with a replication count of 1. And you can see that the Twitter Hadoop server is running circles around our baseline server in this particular case, and that's specifically because the replication count is 1. Maybe I need to step back here quickly and explain what the setup was on both sides. So these were relatively small clusters, both 100 nodes each. For the Twitter Hadoop server, it was a slightly dated stack, or both of them were slightly dated stack. This was CentOS 5.5 and rather than the CentOS 6.3. And still running the Sun 1.6 JRE instead of our Twitter 1.7 JDK. And this is also a slightly older version of Hadoop 2.0 that we're running at the time for these particular tests. So we have 2 clusters side by side, both about 100 nodes. That's when we ran these tests. Then for a TeraGen with 30 terabytes and a replication factor of 3, you can see that the baseline server that ended up running in about 6 hours, and on the new nodes that ended up running in 4.5 hours. So that was, again, much, much faster. And similar results you can see for TeraSort. And then we started saying, like, well, what happens if you run multiple of these things in parallel to see? Because the older hardware had more cores and were wider, larger machines that in theory you can run more stuff on in parallel. And even there, you'll see that the Twitter Hadoop server ended up doing much better. So then we said, well, this is all great, these generic benchmarks. This is very good, but what happens if we just take some of our applications? So we ended up taking one of our typical smaller applications that we were running and a typical much larger application. So that's just application 1 and 2. And you can see, even on our applications itself, it ended up looking very promising and looking very, very good.
We got this backward, didn't we?
So this is a slide with a lot of information on it, and I'll dive into the details of what it looks like. But in general, you can look at it, the higher numbers are better because it's higher throughput. And the blue lines are the Twitter Hadoop servers, and the red lines are baselines. So you can see with Twitter Hadoop server, without. With is good, without not as good. With, without. So in general, what we're showing here is 4 diagrams. On the left-hand side are compression for LZO. On the right-hand side is decompression. On the top, you can see compression at LZO level 3. That's the algorithms we use on our data warehouse clusters when we need more space. On the bottom is more the ones, the default settings that run much, much faster. So if you look at the graphs on the left, they end up running faster. And then you see different columns for how many of these things we're running in parallel. So clearly when you're running only a few in parallel, the Twitter Hadoop server, because it's only single socket and a smaller server, it ends up being much, much faster. So the differences are leveling out a little bit as you run more of these things in parallel. And as you go in and saturate the nodes, again, there will be some difference because these servers end up just having a higher throughput. So these numbers look really, really good. All right, so to quickly recap. Started out originally with one large cluster with a few pieces, and then we decided to split it out. So at some scale, if you have 10 nodes or if you have 100 nodes, you should just stick it all together, have one cluster, and have everybody use it. But at some point, when you start scaling, it starts making sense to break out your clusters. In our cases, we ended up breaking out an RT cluster, a processing cluster, a data warehouse cluster. That's a little bit more like the Wild West, where people run ad hoc jobs and people run all these crazy analysis things that are running there. We have a cold cluster to store the long tail of data. A backups cluster that's not really used for MapReduce, it's just purely for HDFS or long storage. And we have separate test clusters to have people try their applications out on first on a smaller scale, and then smaller experimental clusters for us to run and try our new versions of Hadoop on and things like that. And then it turns out that if your clusters are large enough, and really depending on your use case, it really may be worth to choose different hardware configurations. So what we're showing here is that a smaller, more nimble server ends up actually running much faster than the larger, bigger server. So in the conclusion, at Twitter, our new Twitter Hadoop server doesn't only save a lot of dollars, which a lot of people are very interested, of course, but from the engineering side also, it is much, much faster. And that's what we're pretty happy with. That's it. Thank you.
Questions?
Yeah. Any questions?
Yes. For the performance throughput you have M capital B per second. Is this bit or byte? I'm assuming it's bit because your cold cluster showed was 1 gigabit.
The test on the compression, that's just compression locally on the machine itself. Is that what you're asking?
Yeah, you have the vertical
Can you go back?
access, the vertical access, yeah, right
Mhm.
here. It's M capital B per second. That's a bit or byte?
Byte, megabyte per
Byte.
second.
Okay.
This is within the machine itself. This is compression on the machine itself. This is not using network.
Oh, it's not using network.
This is
Okay.
compression on the machine itself. This is LZO is happening on the machine in this
Okay,
particular test.
the second thing, you mentioned using the 1230 V2, which is an Ivy bridge.
Correct.
Are you looking forward to move into the V3, which is the Haswell?
We would be investigating that, correct, yes.
Okay.
Yep.
Are you, I mean, my question is, you think you're going to get performance increase?
We've just reached this place, but we are always looking to go forward. But I think we would be favoring fewer faster cores for the Hadoop type of application.
Okay, thank you.
Yeah.
How do you define a cold cluster? I was wondering why you need compute, so much compute on a cold cluster.
You don't necessarily need an enormous amount of compute on the cold cluster, but depending on how you store your data,
Okay, but you said
may have to
run
do-
a significant amount of map-reduced jobs on a cold cluster?
there's a significant amount of computation that may be needed if you end up having, depending on what kind of encoding you're doing, you may have to recover files and do computation there. But it's definitely less than on your hot cluster.
I see, okay.
So regarding your use of 10 gigabit Ethernet in the rack, I mean, I've
Yeah.
heard it said that when you go from gigabit to 10 gigabit, that locality becomes a lot less significant, kind of node level locality. Have you quantified the performance benefits of using 10 gigabit in your rack, or cost performance?
So cost, yeah, we sort of have a decent idea of the cost. The A/B comparison, we haven't been able to do yet because we then have to create two clusters with everything else being the same, and one being gigabit and one being 10 gigabit. And we have not done that to scale yet.
Right.
Yeah.
So you just went with 10 because you figured you'd eventually need that capacity?
Yeah. And the cost that we thought we could hit was reasonable.
Right. And even if you don't end up accessing the blocks locally, even when you're just writing files, there's more traffic within your racks than outside of the racks due to the nature that the pipeline is set up, where the first copy is written locally, and the second and third copies are written within this, two different nodes in the same rack. So even in normal write cases, you end up having that situation.
So you guys mentioned that the test cluster was a smaller configuration, was a different configuration. So was just curious as to how do you do the performance, sort of measurement before applications actually go into production itself, understanding the performance characteristics, as well as debugging issues, because sometimes it's tied to the hardware itself. How do you do that in the test cluster when the test cluster is separate or has a different configuration?
Sure. So I think there's two questions in there, right? So first, how do we do performance comparisons? So we start out with the more generic benchmarks, and you try to run those. And then after that, we started running more specific applications that are actually there and comparing. And of course, you have to do some scaling up because the clusters are not exactly the same size. That's something you have to take into consideration. That's a separate aspect from the fact that we have larger processing clusters and data warehouse clusters that have many tens of petabytes of data and thousands of nodes, where you want your customers to try to run their MapReduce jobs on a smaller test cluster first. So running on a couple of hundred nodes cluster still gives you a reasonable amount of scale, but ends up being much less intrusive if people do something bad. So an example of that would be that somebody has a data set and they're getting creative and they decide to set a 2 megabyte block size because they want to have more mappers. That's better to do that on the 200 node cluster than on a several thousand node cluster where they have a massive impact on the large name nodes that are under much more pressure. Does that answer your question?
Partially, because in our setup, one of the issues that we are facing is that the performance characteristics is very different than the data warehouse, as you said, where there is ad hoc queries versus the production, where there are known applications which are running, right? And so you land up facing different issues in these clusters, and you need to debug them. And we are sort of considering setting up sort of equivalent to data warehouse and equivalent to production for test. And I was just curious as to, you don't have that kind of a setup. How do you really debug issues or look at performance characteristics? The performance characteristics are very different.
Sure. One way we do that is with HRAPEN, where instead of looking at individual jobs, how they're running from wall clock time from start to end, you're looking at overall things like overall amount of reads done, overall amount of bytes written and read, and overall amount of millis spent. A lot of times is comparable. But yes, there are differences between a larger cluster that is running tens of thousands of jobs versus a cluster that's much smaller, only several handfuls of jobs in parallel. So that is an interesting challenge. Yes, we have thought about and would like to have equivalent side clusters for testing that are sitting around. But as you start scaling up to thousands of nodes and many tens of petabytes, that's not necessarily cost effective. So you'll have to deal with what you have to deal with.
So what is the disk performance in terms of the 7200 or 10K or 15K? What is the size versus?
So all of the disks that we talked about were 7200 RPM. We did mention the boot SSDs. That's, of course, an SSD.
So you didn't try with 10K?
No.
Do you guys run HBase on any of these clusters? And did you notice any special performance implications of running HBase in terms of hardware?
Yes, so HBase runs on the same. So this Twitter Hadoop server works really, really well for the processing case. And the same configuration that runs for the processing case really well works very well for HBase as well, where you don't need quite as much memory. You don't need the 72 gig of RAM. 32 gig of RAM is sufficient. Having a very much faster throughput on individual tasks and pieces running there, and so being very efficient and having a lot of network bandwidth as well. So that style server for the processing cluster is very applicable for HBase as well.
And did you try running processing and MapReduce together with HBase on the same servers?
That's how we started out with originally, that the HBase cluster was part of the data warehouse cluster, and that we didn't have great results with that because there's just lots of interference, so you're much better off if you can split that out into a separate dedicated cluster. So we do have that split into separate dedicated clusters.
Another 10 gig question. It looked like from your chart that your oversubscription rate on the 10 gig setup was 10 to 1 versus like 2 to 1 in the gigabit scenario. Have you measured your uplink saturation utilization and also during a failure scenario when you lose a fault?
Our large-scale clusters, there haven't been up for that long to get that sort of insight.
Okay.
Yeah, but there is a difference as well, though, because even on the 10 gig, you can use the full 10 gig to connect back and forth, whereas on the bonded 2 gig, the overall aggregate bandwidth is that, but each individual point-to-point connection is still, from source to target IP, is still 1 gig.
Right, I'm thinking inter-rack.
Between different racks, yes. There's a different oversubscription there.
Implying that you're not using the full 10 gig rack to rack, right? I mean, when you're doing 10 to 1, rack to rack effective, it's really more like 1 gigabit at that point, server to server.
Correct, yes.
At any moment in aggregate for the whole rack, yes. But when you're doing one write pipeline, and not everybody's doing rack-to-rack communication, at that time you do have higher bandwidth with the 10 gig then. Yes, yep. No, even between the two racks, right? So between the two racks, in the baseline setup, we end up having 2 times 1 gig bonded, and then there's 2 times 10 gig coming out of the racks. In the other setup, there's 4 10 giggies coming out of the racks. But yeah, it is true that if everybody were to fully run on the network, there's a different oversubscription ratio.
And I'm just curious what you see in terms of saturation. It sounds like you haven't measured it yet.
Not yet, yeah.
How much was the Hadoop configuration different between the two clusters? Or did you use the same configuration?
For the performance, the side-to-side configuration was the same version.
But the fine-tuning, did you do any fine-tuning on the Hadoop configuration? Number of threads and Hadoop parameters, did you tune them at all? Or
number of slots.
Number of slots, number of server threads for...
Most of the operating system setup were relatively standard, and then the applications themselves would really drive what kind of things was going on. So on some of the applications, there's more things going on depending on what you do. If you do test TFSO, there's just more, you're driving more of the I/O rather than more MapReduce slots.
Okay.
Hi there. Very interesting data.
So my question is specific to the characteristics of the benchmark application 1 and 2. So what are the characteristics? Is it like it runs whole MapReduce jobs all the time? Does it run one map job, two map job per application? What is the distribution?
I don't have all of the details, and I'm not sure that I can go into all of the details between the exact application differences.
I'm just curious about the distribution. Like, does it run MapReduce job all the time on the cluster, or is it like small jobs, like one map?
No, I think during that time the cluster is pretty busy. So the entire cluster is saturated at that time and is very busy running multiple jobs. So everything is running at the same time there. So it's not that you're running one job and the cluster is sitting doing nothing and then something else is going on.
As an example, we did run pigmix on both clusters. We didn't present the data, but pigmix had similar behavior also. Yeah.
Thank
you. Two questions. I think on slide 9 you talked about some I/O bottlenecks, and with the THS, looks like you don't seem to have them. Can you elaborate?
Yeah, that was very specific to that particular server from that vendor, and we realized it downstream. So I cannot comment on. So that was specific to an issue.
Okay, wonderful. And a more general purpose question, like, what is the cluster utilization you see typically as a percentage?
There's 5 clusters.
Are we talking about CPU, or are you talking about?
Yeah, it's a compute primarily, yeah.
Yeah. So our clusters are pretty highly utilized, almost surprisingly high. Earlier on, it was much higher because we were using a very high version of LCO compression. So then we're talking about 70–80% utilization on CPU. That has dropped a little bit since we've tuned that down a little bit. But in general, like how busy the clusters are, they're all the time, very busy. Particularly the data warehouse cluster where there's ad hoc load just driving this. On the processing cluster, it works slightly different. We really only allow people to run stuff that they have allocated capacity to. We use HRAVEN to monitor that and to keep people within bounds there. But on the data warehouse cluster, for example, one of the days we had an incident where part of the tools that help drive some of the load on the data warehouse, typically half the load of the cluster were down. The cluster was still just completely full. So those clusters are very full, very busy, and running very hot.
Thanks.
What about hardware failures? How do you monitor them?
So Twitter has an observability system for that, and Hadoop is no different. Plug into the same one.
Right, and as one of my colleagues pointed out yesterday during his talk, we use a health script that you can configure in your task trackers to be able to check if clusters are doing well.
Thank you. I have 2 questions. The first one is, now that you're using the Ivy Bridge, you are constrained to 32 gigs, correct?
Yeah.
So do you think you will benefit if you have more? I mean, it's a speculative
yes,
question.
Yes. We would like more memory on that type of processor if we could get it.
So your ideal platform will be low number of cores, high frequency. This is a 3-point something. And 16 hour memory gigs.
Yes. Your thoughts are aligned with where we are going. Yes.
Okay, great. And the second question is, have you explored hardware compression as opposed to software and CPU impact, or you don't, or because you mentioned that you have 2 LCO parameters, correct?
Yeah.
Because you don't want to use that much CPU in one of those clusters. So I just want to know what have you explored on hardware, or do you think it's too costly for this? Thanks.
We haven't gone into a lot of details on the hardware specifically for compression. But the reason why we're using 2 different is if you're more storage bound and your clusters are like 85–90% full, then you want to spend a little bit more CPU and you want to trade off some CPU against less space, particularly if you're writing files once and read them many, many times. Yeah. On your processing side, when you're writing them once and then reading them not as many times, and you're just really interested in throughput, then it's a better trade-off to have higher throughput on your compression and maybe give up 10–15% on the file size.
Okay, thanks.
Hi. Thanks. Great talk, actually. I have a few questions. Number one is, can you talk a little bit about the I/O weight or CPU utilization or efficiency on your current edge, the Twitter Hadoop nodes?
I think we're struggling because there's multiple Hadoop clusters.
Sure. Let's talk about the production one.
So why don't you come to our Twitter booth at
Yeah.
26 and we can talk more detail on some of these things.
Thanks.
Quick question. Do you have any statistics on rebuild times in case of a node failure? If you have a full node failure with your architecture, how much time does it take to get back to operation on 3x replication?
So Dan talked about that a little bit in the discussion yesterday. That really also depends on cluster size.
Right.
If you have a smaller cluster size, then the number of nodes participating in rebuilding or re-replicating those nodes is different, which is slightly different from how fast that node takes to reboot back up. And the aspect there is the number of inodes that you've configured, and or if you have disk failures and FS checks coming on. But I think we're running out of time. We're interested to have more questions and discussions. We'll go over to our booth 26. Thank you.